Welcome back to the Mechanics of Solids lecture series. We're looking at examples related to torsional stress and rotation in shafts. The next example that we're going to look at is problem 6.18 from the Mechanics of Materials textbook by Timothy Philpott, Wiley, 3rd edition. This is an example of a gear shaft assembly where internal torques are transmitted to each of the different shafts through external torque loads that are applied by the gears. Okay, and the problem reads: a solid steel shaft of variable diameter is subjected to the torques shown in figure 6.18. The diameter of the shaft in segments 1 and 3 is 50 millimeters, and the diameter of the shaft in segment 2 is 80 millimeters. Let's go ahead and write that down as part of our given. So we're given D1 equals D3 equals 50 millimeters, and D2 equals 80 millimeters. And these are solid circular shafts this time. We are also given that the shear modulus for the material, the same in all of the shafts, is equal to 80 gigapascals. And it says the bearings allow the shaft to turn freely. Part A, we are asked to find the maximum shear stress in the compound shaft. So in other words, find tau max in any segment. And of course we should consider all segments. To solve for tau max in a particular segment, we use the formula tau max equals T, where T is the internal torque, times R over J for that segment. So the way I would like to approach this, the way I recommend you approach this, is to draw an internal torque diagram so we can figure out what this T value is for every segment of the shaft. I'm going to convert this picture that we have up here to a free body diagram so we can easily draw that internal torque diagram. Okay, so starting from point A, here first let me put in my lengths: 0.7 meters, 1.8 meters, and 0.7 meters. This is point A, B, C, D. Okay, so I have a torque of 1200 Newton meters applied at point A. When looking at this direction of this torque with reference to some fixed point, it's going to cause segment 1 to rotate according to the right-hand rule. So we call that a positive torque on the end, and I will draw that one going outward, 1200 Newton meters. Okay, we come along to point B. That torque is acting in the opposite direction, so I'm going to draw it acting to the right. Point C is acting in the original direction again, same as point A, so I'll draw it going to the left, 2800 Newton meters. And finally at D, also acting the same in the original direction, 500 Newton meters. Okay, so now we can draw our internal torque diagram, label it as torque with units of Newton meters is fine. Okay. Point A, this is positive. The arrow, double arrow going outward, is positive torque, so it jumps up by 1200 Newton meters. Point B, the torque is acting in the opposite direction, so we know it's going to jump down. 1200 minus 4500 is negative 3300. Positive in segment 1, negative in segment 2. We reach point C. The torque is going to jump up by 2800. Negative 3300 plus 2800 is 500. And finally at the end it jumps up by another 500. And this is a good check for you because you see that the torque diagram comes back to 0, and it should always return to 0 at the end if you know every single one of these applied torques or reactions. Okay, so now we can proceed to solve for the stress. I want the maximum shear stress in any segment. Looking at my torque diagram and looking at my diameters, D1 and D3 are the same, so I know the stress in segment 1 is going to be larger than the stress in segment 3. I don't need to evaluate segment 3 there. Okay, so I'm going to evaluate tau in segment 1 for sure, and in segment 2 the torque is larger. The diameter is also larger than segment 1, but I can't tell which one is going to control, so I'll go ahead and evaluate both of them, tau 1 and tau 2. Our working units for this problem, we want to solve for our stress in megapascals. Should have indicated that up here. So our working units are going to be newtons, millimeters, and megapascals for stress. Okay, starting with segment 1, we need to compute J in order to compute tau max. J1 is equal to pi over 32 times d to the 4th for a solid section. Pi over 32 d1 is 50 millimeters taken to the 4th. This gives us, rounding to 3 significant digits, 613,000 millimeters to the 4th. Therefore, tau 1 equal to T. The torque is given in Newton meters. I'm going to convert that to Newton millimeters by multiplying by 1,000. 1,200,000 Newton millimeters times the radius, half of the diameter, 25 millimeters, divided by this J value, 613,000 millimeters to the 4th. Notice that millimeters and millimeters on the top reduces the bottom to millimeters squared, and then I have a Newton per millimeter squared, or a megapascal, which was the unit I was looking for, and those numbers compute to 48.9 megapascals. To save some time, I'm just going to talk through, for member segment 2, we would evaluate J2 with the same formula using a diameter of 80 millimeters this time. That computes to 4,021,000 millimeters to the 4th. Tau 2, the shear in segment 2, using the same formula, this time with a torque of 3,300 times 10 to the 3rd Newton millimeters, the radius half of 80, 40 millimeters, and J2 as we just computed. This number computes to 32.8 megapascals, and we see if we compare these two numbers, tau 1 is clearly larger than tau 2, so tau max in any segment is 48.9 megapascals. My logic or sanity check, I have stress less than yield in most typical materials, but large enough to be reasonable value. I have the right working units, megapascals, and so the answer appears to be correct for our sanity check.